Welcome. In this lecture, we will focus back our attention to tolerances, limits, and fits. So it is the last short segment of a series that we dedicated to this subject, and here we will focus more on the idea of potential failure if the press fit or shrink fit is too tight. So we're going to look at shrink and press fits, and then study the interface pressure if we have a lot of interference or a significant amount of interference, and we have an example to illustrate that. So going back here, the layout of the press fit is a general layout where we have a shaft, and the shaft in general can be hollow. So the shaft itself has a bore, and in case we have a solid shaft, obviously we can shrink that inner radius to 0. The outer radius still there, and the outside dimensions of the shaft would be such that it can interfere with a cylinder. So if I have a cylinder and the cylinder has walls, these are the walls of the cylinder in the cross section. This is another view, another cross section of the cylinder walls. And the shaft is the light blue that you can see here on the screen. And the shaft has dimensions slightly bigger than the outer dimensions of the shaft are slightly bigger than the inner dimensions of the cylinder itself. So it's a general idea, and based on that, an interface pressure is developed once we find that interference. So the interference that we will find is delta, and the amount of the interference is obtained depends on the difference between the dimensions of the shaft and of the cylinder or the hole. So we would have to figure out what is delta minimum, and delta minimum is the minimum interference, and that would be the diameter of the shaft, that is the smallest, minus the diameter of the hole, that is the largest, and that will give us the smallest amount of pressure. So this is small pressure. And delta max would be the difference between the shaft diameter, that is maximum, minus the cylinder diameter, that is minimum, and that gives us maximum pressure. So in both cases here, an interfacial pressure is developed. An interfacial pressure is developed such that we have a very long formula for the interfacial pressure if the materials of the shaft and the cylinder, the surrounding cylinder, are different. So in this case, we have to consider that we have two materials, and the two materials, let me just get this here. So the two materials are, we have the shaft material, and the shaft material is inner, so it takes the symbol I, and I have the whole material is outer, and that takes the symbol O. And the geometry is described by an inner radius of the shaft, an interface radius between the shaft and the hole. This interface radius is a common radius, and then an outer radius of the cylinder or the hole. So 3 geometric parameters that we have. And the materials are described by a number of elastic constants. Each material is described by 2 elastic constants, and the 2 are the Young's modulus for the inner, the Poisson ratio for the inner, the Young's modulus for the outer, the Poisson ratio for the outer. So I have 4 parameters describing. If it turned out to be that the shaft material and the hole material are the same, so we have only 1 elastic constant, E, and then another elastic constant, nu, for both of them, and these 4 will become only 2, E and nu, for same material. So if I come to the geometry back again, I have R inner and interface R and R outer, and moreover, I have also an important parameter here, which is the interference amount that I have to compute. And the interference amount is, as I mentioned, it will be minimum amount that causes the least pressure in case we have, for example, the shaft is rotating and the cylinder represents a flywheel, and the flywheel needs to be press fit, so it has to be always in contact with the shaft. So as the shaft rotates at higher and higher speed, then we may lose that contact. And that's an important design problem that we'll get into a little bit later. For now, these are the conditions that we have. We have 4 geometry parameters, 4 material parameters, and the pressure that is computed is dependent on both the geometry and the material parameters. So the pressure of the interface is given by this formula. You have it in the slides. But what I would like to mention here is that delta has the units of length in meters, and R has the units of length in meters. So if we have this ratio delta over R, this will be dimensionless. It's similar to a strain. So if you multiply a strain by an elastic constant like Young's modulus, you would get essentially a stress. So the units of the stress will be reflected by the units of the Young's modulus, because you have 1 over E0 here, 1 over I here, and those will kind of flip over and give us the units of the stress. So this equation, in case we have E equals to E outer equals to E inner, and we have nu equals nu outer equals nu inner, then this equation becomes much simpler, and the simpler equation is given by here. And if you look at this equation here, then we have the pressure is equal to E delta over 2R cubed times this factor in between. This is a geometric factor that has the dimension of R squared. So when everything cancels out, then we have the units of the pressure will be the same units as the elastic modulus of elasticity, or Young's modulus E. So let's take an example here, an example on the press fit. And the press fit here is an example that we have a table that lists the maximum and minimum hole and shaft dimensions for a variety of standard press and shrink fits. So we selected just one of these examples because there's so many of them. They are very similar, and the materials are both the same, the hot rolled steel. So we have the steel properties. The Young's modulus is 207 GPa, and a Poisson's ratio is close to 0.3. And we want to find the maximum and minimum values of the radial interference and the corresponding interface pressure. So we want to find delta min and delta max, and based on that we plug it back into this formula here that we highlighted. and then we plug it in this formula, then we get the interface pressure. So we again maybe highlight. So now let's consider the procedure to do some computations for both loose fit and press fit. So taking a couple of examples to show the procedure. So the first thing we want to do is determine the dimensions. So the dimensions are basically 4 different numbers that we would consider. And we would have to calculate D min and D max, capital D max. And for the shaft, we would have to calculate lowercase d min and lowercase d max. And that depends on whether we have an interference or a clearance. In order for us to do these computations, we need to identify 2 numbers. One for the tolerance and one for the degree of interference. So for the tolerance, we have here the IT grade number. And for describing whether we have a deviation, then we consider to find one particular number that describes a deviation, which is the fundamental deviation. So the IT grade number gives us delta D, lowercase d, or delta cap d. And the fundamental deviation is all what is needed, and the fundamental deviation is used either if we have a clearance, then we would have to subtract because it's a negative number that we would obtain. If we have an interference, then we would have to add. And because we have positive value for that interference. So for this summary, we would, let's consider now the procedure that we have and consider a couple of examples. So the procedure is that we go to table A11 or A13, depending on whether we have metric or inch system to find the IT grade numbers, and that gives us delta cap D, delta lowercase d. And then we go to table A12 or table A14, depending on metric or inch. And that gives us the third number that we use, the third quantity, that is the fundamental deviation for the shaft that we consider. And then we can proceed to determine for the hole, the minimum dimension is the reference, capital D. The maximum dimension is the reference plus the delta cap D that we have obtained from the table A11 or A13 for the IT grade. So it depends on the IT grade. Now we have 2 possibilities. Possibility number 1, for the shaft, if we have a clearance fit, then the letter code is C, D, F, G, and H. And the D max is the reference, lowercase d, plus delta fundamental, which is negative, and D min would be lowercase d, the reference, plus delta fundamental, which is negative, minus delta d, which is the tolerance for the shaft, which is also negative. So 2 negatives. So we rewind here twice in equation 737. And for the shaft with interference fit, the code is KNPS and U. And again, here the D-min is the reference plus delta fundamental, so it's a positive number. And D-max, we add the delta fundamental and the tolerance delta D, so 2 steps up. So it's either 2 steps down for the clearance or it's 2 steps up for the interference. So let's apply that and take numerical examples to see how it works. The first one is just let's determine the dimensions without worrying about pressures at the interface. So the dimensions, we will do that for an interference, and then we'll do that for the clearance, just to kind of see the comparison or the difference. So for the, we have an ISO symbol 34H11C11. So that is metric, so the reference cap D equals to lowercase d equals to 34 millimeters. So this is the reference for the shaft and for the hole. And then we'll go from there. We wanted to determine delta fundamental, and we want to determine delta lowercase d and delta cap D, 3 different quantities. So we have here the IT grade is 11 on both sides for the shaft and for the hole. So in this case, the tolerance is the same. Delta lowercase d equals delta cap D. And looking at the table, the amount of the deltas is 0.16 inches. So that gives us immediately the dimensions of the hole, because the minimum is the reference, the maximum we just add the 0.16 inches. Now we go to the shaft. The fundamental deviation is a C, so the code is C. And when the code is C, that translates to delta fundamental from the table minus 0.12 inches. So in this case, we have the D max, since it is a C code, it means it is a loose fit or a clearance. And we have to rewind twice. So the first time is minus 0.12, and the second time is minus 0.12, and then minus 0.16 that we obtained from the tolerance. So in this case, the maximum value of the diameter of the shaft is 33.88 millimeters, and the minimum value is 33.72 millimeters. That solves the problem. Next, we'll consider a problem on a medium dry fit. So medium dry fit now is the opposite to this example. So this example is it was a loose running fit, Now we're going to go to a medium dry fit. So medium dry fit is an interference problem, and therefore instead of rewinding twice, we're going to have to step up twice for the shaft. Same procedure. Here, the basic size is 2 inches, so it's all in inch units. So we have here cap D equals lowercase d equals 2 inches, and then we are not really given the code, the IT grade and the code, but we're given the terminology for that fit. So the terminology is a medium dry fit. So medium dry fit, when we look at how it is described from a design perspective, the table 7.8 will give us the designation that it is actually an H7S6. H7S6. So it's a hole basis. The IT grade for the hole is 7. The IT grade for the shaft is 6. And it's, the interference code is for the fundamental deviation is S. So these are the three things that we need. So for IT grade 7, the delta cap D is 1/1000th of an inch, 1 mil. And for the IT grade 6, for the shaft, that is delta lowercase d is even less than 1/1000th of an inch. It's 0.0006 inches. So we got 2 out of 3. Because it's an S, so the fundamental deviation is 0.0017, that's the third quantity. And then we can go into our computations. So the D max, we add the delta D to get the maximum size of the hole is 2.001 inches. For the hole minimum dimension, it is the basic size. Now we turn our attention to the shaft. We're going to go 2 steps. So one step is we add the fundamental, which is 1/1000th of an inch. 0.0017 inches. That's the fundamental deviation that we got for the S. So S translates to 0.0017 inches. And then we step up one more step with the tolerance for the shaft, delta D, we added 0.006, and that gives us dry fit. So the medium dry fit will have some internal stress that we will compute later on, but we'll take an example to illustrate how we would compute the interface pressure between the shaft and the hole. So let's consider the last example here is a press fit problem, and in this press fit problem, we wanted to just compute the minimum and the maximum value for the interference between the shaft and the hole. So we have a fit designation given to us as 50 H7 / P6. This means that the first 50 would translate to lowercase d equals cap D is equal to 50 millimeters. And the 7 is IT grade 7, an IT grade 7 for the tolerance. And the 6 is IT grade 6 for the tolerance of the shaft. And the P code translates to the fundamental deviation. So with these 3 numbers, the dimensions are already computed and given to us here. The basic size is 50. The maximum hole diameter is 50.025. The minimum hole diameter is the same as the basic size. The maximum diameter for the shaft is 50.042. The minimum dimension for the shaft is 50.026. And the next question is, how are we going to compute the dimensions? So we have here delta, right? So delta, which is not really a fundamental deviation, is just a symbol now for the amount of interference. So we're going to use the symbol for radial interference. So radial interference, we have a max and we have a min. So let's just kind of think about the max. The maximum interference would occur if I take the shaft diameter that is the largest and subtract it from the whole diameter that's the smallest, right? Not only that, but I have to divide that difference by 2 because the diameters are twice the radii. So it will be 1/2, and now this will be lowercase d max minus cap d min, and that in this case 1/2, lowercase d max is 50.0442, and the cap d min is 50, and that can give us the interference radial between, which we can use to substitute in the formula that we developed for the interfacial pressure. And we note here that the materials are not specified in this case, but if we assume they're the same, then we just need 2 elastic constants, one Young's modulus and one for Poisson's ratio. So here is the solution. Poisson's ratio for the steel is close to 0.3, it says 0.292. For the steel, the Young's modulus is 207 GPa, and from our calculations, we now can find the pressure if the radius is half of the 50 millimeter. The basic diameter is 50, so the radius is 25 millimeters. And here is the E, and here is the radius in meters. So you have to convert 25 millimeter to meters to 5 meter because we're using basic MKS units, SI units. And notice that I have here cube, and then the radii here are included in the formula. So at the end of the substitution, the pressure, interfacial pressure, depends on how much interference exists, radial interference exists between the 2 radii. And that comes to be 3,105 delta. So the formula that we got was in these units, and the value is in megapascal, and delta is in millimeters. So with that, we can now use the lowercase delta max, the maximum value of interference, and the minimum value of the interference, as we mentioned before. And we're going to use these 2 values, substitute into this equation here, and get 2 values for the pressure. For the maximum value of the interference, the pressure that's recomputed according to these calculations is 65.2 megapascal, and that's a very high pressure, because we know that in a power plant, for example, if we just have a pipe containing extremely high pressure water for cooling, it's usually on the order of 8 megapascal. So this is almost like 8 times, close to 10 times what's used for high pressurized water, for example. Very, very high. So it can lead to, definitely can lead to potential failure, and that subject we're going to keep for the next, sometime in the future, where we develop formulas for the Hooft stresses and the radial stresses and the effective von Mises stress that would lead to failure. So we'll do that a little bit later. For now, we just are content with computations of the maximum amount of pressure and the minimum amount of pressure that exists. And with that, we come to the conclusion of these few segments on limits and fits in press fits and in mating parts. And we have concluded now the introductory part of the course, and we're ready to move on to the project and to move on to material and mechanical properties in the next lectures. So with that, we will end the segment on limits and fits, and thank you for watching.